So let's say we've found local maxima in the accumulator array that are greater than a threshold. So we have this array called A peaks, which contains ones that are the peaks that we're looking for. So we want to find those coordinates, and we can use MATLAB's find function again. Unfortunately, we just can't use find on the array and get back the coordinates. In terms of this case, there's three sets: row, column, and the depth coordinate. For some reason, they implemented this only to find coordinates of two-dimensional and one-dimensional arrays. However, we can still do it because we can always treat a multi-dimensional array as a one-dimensional array. And this is actually how they're stored in a computer. So you can think of a two-dimensional array basically as a set of rows like this. Inside the computer, they're just stacked up in order like that. So in the case of three-dimensional, of course, we would have these rows stacked up for the first slice, and then for the second slice, and the third slice. But the point is that the values have a one-dimensional index when you think of the array as being stored like this. So find, if you pass in a multi-dimensional array, it will just return these one-dimensional indices like this. You can still get back to the equivalent subscripts or indices of the 3D array using this into sub function, indices to subscripts function. You pass in the size, which returns the number of rows, columns, and depth, and you pass in the indices that you want to convert, and then it will return the equivalent row, column, and depth indices. So this is the code that does that. Here is the dilation test to see if it's greater than a threshold. Here's where it finds the one-dimensional indices, converts it to two-dimensional indices, or I'm sorry, three-dimensional indices, and then draws the parabolas on the image. And it does that just by going through the equation of parabola and computing x and y. So let me paste this code into the program after the part we already have, and run that. Okay, so this is the part we had before, namely we got our original image, edge image, a slice of the parameter array, and then these are the parabolas that were found. So in this case it found 1, 2, 3, 4 of them, it looks like. By adjusting the threshold, you can find more or fewer of these parabolas. Just a couple other notes on the Hough transform. You can make it more efficient by using the gradient direction. So right now, up to now, we've just used the location of an edge point, but most edge operators will return a direction as well. So if you use the gradient direction, that is essentially the same direction as this perpendicular vector. So basically that determines this angle theta here. So in other words, we don't need to loop over angles because we already know the angle given an edge point. So that saves one for loop, which greatly speeds things up. It is possible though that the gradient angle is noisy, in which case your line angle would not be accurate. So it might be better to increment multiple cells corresponding to several angles near that estimated angle. The generalized Hough transform is a nice extension to the line and curve finding. Can find arbitrary shapes. We do some pre-processing. We take our shape and we represent it by a bunch of boundary points. And for each boundary point, we compute the distance and angle to the center of the shape. So all that is pre-processing. So for example, this shape here, we've got 2 points, this one and this one. They both have the same angle, gradient angle. So for that gradient angle, we note that the vector to the object center is in this direction. It's R1 and R2. So we create a R table, namely for each possible gradient direction, we store the vectors pointing to the object center. So in this case, we had these 2 points. They both had the same gradient direction, so we list both vectors here, R1 and R2. So to find the shape then, we compute the gradient direction at each endpoint. We look up the vectors from the R table. These point to the possible center. And then we increment the accumulator array at those points. Here's a synthetic example of here's our template object, so we construct our R table from that. Here's a test image containing a couple of those objects. And this is the accumulator array that specifies the object centers. So we just look for peaks in this, and we could see there's 2 of them here.